Okay, welcome back from Thanksgiving break. Let's do some problems here. Remember what we've done previously. We want to expand this log. So let's go ahead and split it up. So I'm going to start by writing this as log base 17. Note all of these logs we write are going to have that same base, 17 there. Log base 17 of my first factor there, log base 17 of 15, plus log base 17 of z to the power of 1/3, but it's a cube root, so instead of writing the 1/3 as a power like that, I'm going to plug it and instead multiply this by 1/3, which is the same as dividing it by 3. So I'm going to write that bit like that. And then I have plus, and notice I have something interesting here because my next term is a y term, but I also have a y term in the denominator. And exponent rules say when you're dividing two exponential expressions of the same base, both base y in this case, you're going to take the numerator and you're going to subtract the denominator. So I have 5 minus 1/2. It's going to be the same as y to the power of 4.5, which I'm going to write as 9 over 2. So I will have plus, again, log base 17 of y, and I could write it as y to the power of 9/2, but instead I'm going to plug it and do multiply by 9 and divide by 2, just like that. And then finally I have my last term there. Since that is in the denominator, I'm going to subtract log base 17 of x, and it would be to the fifth, but again I'm going to plug it and say minus 5 log base 17 of x, and that is how I'm going to leave my final answer. Except I notice I made a mistake because down here that was a negative 1/2, so this should have been a negative 1/2 right there. 5 minus negative 1/2 is the same as 5 plus 1/2, which would be 5.5, which would be 11 over 2. So I need to change that to an 11 right there. But other than that, I think now I should be good. Very similar idea on this one, except instead of expanding the log, we will be compressing it. So first thing I'm going to do is I'm going to use the plug rule in reverse and throw those coefficients on top of those variables there and write them as exponents. So I'm going to do that to all these terms, but then notice this term at the end is kind of goofy because I have log base 2 of 4. Well, log base 2 of 4 is saying 2 to what power gives you 4? Well, 2 squared gives you 4, so log base 2 of 4 is really just 2. So I can unplug it like that. And now, since they all are base 6, I can say log base 6 of h to the power of 8 times, what do I have here? J to the power of 4/5. And now I have subtraction, so that's going to correlate to division. So I'm going to get k to the 17th, and then I will get x squared, just like that. And that is how I'm going to leave it. So now we're going to actually do a problem here using logs. On the day of a child's birth, a deposit of $25,000 is made in a trust fund that pays 8.75% interest. Let's remember that 8.75% is the same as the decimal 0.0875. So that is going to be my rate. And we're told that is compounded continuously, which is, of course, telling us that we're going to use our PERT equation, or the poked equation, however you want to do it. So the amount in the account will equal the initial investment, the principal amount, times e to the power of our rate times time. And we want to know the amount after 25 years, so on the 25th birthday, which is going to be the principal investment of $25,000. $200,000. So someone really loves this kid, times e to the power of our rate, which is 0.0875, times time, which is 25 years. And we're going to crunch those numbers and get, after 25 years, that spoiled little child will have $222,000, $822.57. I said that weird. Whatever. It's late. I'm tired. But that is the power of compounding interest right there. So now we're going to do a similar problem, except this time we don't know the rate. So we need to find the rate here. But we do know that we have a culture of bacteria growing. Initially, there are 230,000 of those little critters, and then 780,000 after 7 hours. And we want to know how many will there be after 11 hours. So again, we're going to use our PERT or poked equation, and we know that the current amount, or the amount after 7 hours, is 780,000. A lot of zeros there. And we know the principal amount was 230,000. And we know the rate is something that we want to find, but we do know that this is representative of 7 hours having passed. So now we need to go ahead and solve this equation. So I'm going to divide both sides by this 230,000 right there. So I'm going to get 7d8 divided by 23. Notice 1, 2, 3, 4, 1, 2, 3, 4. All those zeros are going to cross off. So 78 over 23 equals e to the power of r times 7. And so I'm going to take the natural log of both sides. 78 over 23 equals the natural log of e to the power of r times 7 is the same as r times 7. But instead of multiplying by the 7, I know I'm solving for r, so I'm going to divide by 7 over here on both sides. So I know that my rate is going to be the natural log of 78 over 23, all divided by 7. So let's crunch that real quick. You'll get 0.174. Notice that the number is positive because the population is growing, not decaying. And you will get a lot more decimals as well. You get 174459231, and that will continue on. So I'm going to use 0.174 to start. I'm also going to store this variable so we can take a look at how much error we get. But now that I have my rate, the question is, how much will be present after 11 hours? So we're going to use that equation again, and we're going to say that the amount will equal the initial population, which is 230,000, times e to the power of our rate, which is 0.174, times our time, which is 11 hours. And now we just need to crunch this in our calculator, and we should get 1,559,435, and then some decimals that don't really mean much to us. If you round it to 0.174, but if you store that value and find an exact answer, you get 1,567,333. So you see, we have underestimated the population by almost 10,000 when we rounded it to 3 decimal places. That is, again, because exponential thingies grow super quickly. That's their nature. That's what they do. So be careful and store your variables when possible. Now we want to look at some half-life problems. So half-life is talking about the time it makes for a quantity to reduce to half of its size. Typically speaking, you are using half-life when you're talking about radioactive decay of isotopes. And so we're saying that the half-life of bismuth 210 is 5 days, which is crazy fast. And we're saying if 100 milligrams are present currently, how long until only 35 milligrams are present? So 100 is going to be our starting quantity. 35 is going, we want to know how long until 35. So we need to figure out the rate of decay. So again, we're going to use our equation that we love. And again, this is exactly the same as the poked equation if you prefer that. But we know the half-life is 200 and, I'm reading fake things. We know that the half-life is 5 days. So we know we are starting with 100 milligrams, and we want to find the rate, but we know that after 5 days, we will have half of what we started with. So instead of 100, we will have half of that, which is 50. And then we're going to solve this just like before to find our rate. But notice what happens. We're going to divide by 100, and we get 50 over 100, which is, of course, exactly the same as 1/2 equals e to the r times 5. That will always be the case in these half-life problems. We will always have a 1/2 over there because it's talking about the amount of time to decrease population by 1/2. And so we get 1/2 equals e to the r times 5, and again, we're going to take the natural log on both sides, and we are going to get this equation right there. So I kind of skipped some steps, but check that last problem to see why we end up with this. And we're going to crunch those numbers. We're going to get negative 0.139. And again, I'm going to cap it there, but I'm going to store that variable and get both answers here. Again, just to kind of see how much error I get when rounding to 3 decimal places. But notice that the rate is negative because we're talking about decay. The bismuth is decaying and reducing its size by 1/2 every 5 days. And key thing here with these half-life problems, you will always end up with this bit right there. ln of 1/2 divided by the half-life equals your rate. So you might jump to that if you want to. But now we want to know how long until 35 milligrams are present. So we want to know how long until 35 milligrams. Well, that's going to be our initial population of 100 times e to that rate, negative 0.139 times t. So we're kind of using it in a different way here, and we need to solve this equation. So we're going to get 35 divided by 100. And again, we're going to take the natural log of both sides, and then we're going to divide this time by that rate right there, negative 0.139, and that will equal the time. And again, check my work and make sure you understand where all of that just came from. I'm doing everything legal that we've learned so far. I'm just not writing those steps down. So check it and make sure you get there too. Crunch those numbers and let's see what we get. And so you're going to get 7.553 days if you round your answer, and 7.573 days if you store the variable and get it exact. Now, that's not all that much difference this time. We're talking about roughly 30 minutes there, so they're pretty close. But again, they are different. So, a series of problems here, talking about a huge application of half-life. Carbon dating, figuring out how old things are. So we're told that the half-life of carbon-14 is 5,730 years. That is a long time, which is why it's a good element to use for carbon dating, because it takes a long time to go away. So, first, before we can do anything, we need to figure out what the rate of decay is. If the half-life is 5,730 years, 5,730 years, what is that rate of decay per year? So we're going to do the same thing. We're going to get the ln of 1/2 divided by 5,730 will tell us our rate. And we're going to get, I want to say it's like 0.00012, which is going to give us roughly 0.012%. And of course, that number should be negative because we were talking about a rate of decay. Ooh, someone's driving down my street very quickly. So we get that rate, and now question number one says, suppose a piece of wood from an archaeological dig is being carbon-14 dated. It is found to have 70% of its carbon-14 remaining. Estimate the age of the piece of wood. So again, we're going to use our equation, A equals P times E to the R times T. And let's think about how this is going to work. How do we deal with the percents here? Well, imagine that the initial population was 100. Let's put these rates in there. Wait, why did I write my rate like that? That looks better, because I don't want it as a percent. I want it as a decimal. So 0012. And this is going to be times time. So again, we're saying, well, imagine if we started with 100. Well, what would be 70% of 100? Well, it would be 70. And then to solve this, the first thing we would do would be to divide by 100 on both sides. And we would get this. But notice, 70 over 100, well, that is 70%. So we just as easily could have started this problem by saying, well, we have 70%, 0.7, equals e to the power of our rate times time. And so we're going to solve this by saying the natural log of 0.7, or 70 over 100, or 7 over 10, or whatever you want to do. The natural log of 0.7 divided by negative 0.00012, our rate, equals the time. And again, let's crunch it and see what we get. 2,972.291 years if you round it to 3 decimal places. But if you go exactly, you get 2,948.504 years, which is fairly significantly different. We're talking about, like 25 years here or something. So again, store that variable. But we have found the estimated age of that piece of wood. And now question number 2 says, how long would it take for an object to lose 25% of its carbon-14? Well, if it loses 25%, that means that it still has 75%. So it's going to be a very similar problem. It's going to be 0.75, and that's going to be instead of 0.7 there, so it's going to be the only difference. We're still going to get the natural log of 0.75 there, divided again by that rate, negative 0.00012, and that will tell us the time, which in this case, if we round, 2,397.351 years, and if you don't round, 2,378.165 years. So finally, one last problem. Suppose a tree fell 400 years ago. How much of its carbon remains? So we're going to get A equals the initial amount of carbon in the tree, which we don't know, so we're going to have to represent that as 100%, which is just the number 1. So A equals, the one doesn't do anything, so I'm going to get rid of it, e to the rate, which is again negative 0.00012, times time, and it was 400 years. So we're going to crunch that, and again, I'm going to give you both answers. 0.95313 if you round, 0.95276 if you don't round. But remember, these are talking about percents, so we can say 95.313% remains, or 95.276% remains. And we're done. So slightly different problem here, getting away from half-life momentarily. We have a function here that's telling us the depreciation of a car. So after t years, the value of a car that cost $20,000 initially is modeled by this equation, v of t equals 20,000 times 3/4 to the power of t. Graph the function and determine the value of the car 2 years after it was purchased, and then express in words how the depreciation of the car is calculated. Let's do that first. Notice this bit right here, 3/4 to the power of t. Well, that's taking that initial value of 20,000 and each year multiplying it by 3/4. So each year the car loses 25% of its value, or rather the car maintains 75% of its value. But each year it goes down by 25%. And so let's graph this function and trace to the x value of 2 and see how much it's worth after 2 years. So we need to graph this, but let's think about a smart window here. And so think about our x value is going to be our t value, the years, and we want to know after 2 years. So I'm going to graph from 0 up to 5 on the x-axis, and then I'm going to hit zoom fit, and it'll give you a nice, pretty graph that looks something like this. And notice I actually erased those axes because it's not even showing me the x-axis, which is totally fine. But now go ahead and trace to the x value of 2, and you should get the y value of 11,250. And remember, we're talking about dollars. So after 2 years, this car depreciated from $20,000 to $11,000 and $250. I keep saying the dollar thing's weird, but that's a lot of lost money, so, be careful. Okay, another half-life problem here, but we're going to look at it in a slightly different way. So now we're saying let Q in grams represent a mass of radioactive radium whose half-life is 1,620 years. The quantity of radium present after 2 years is given by the equation Q of T equals 25 times 1/2 to the power of T divided by 1620. Question number 1 says determine the initial quantity of radium. Well, the initial quantity of radium is going to occur when the time is 0. So if you think about this equation right here, the numerator of this bit right here is going to be 0, which is going to make that whole fraction 0, which is going to make this whole thingy 1 right there, which is going to tell us that the initial quantity is 25. So in that regard, this equation is working in the same way as our other equations, and that initial population is out there as a multiplier. So the initial quantity of radium is 25, and then determine the quantity of radium present after 1,000 years. So we're just going to plug in 1,000 to t right there and see what we get. In looking at problem number 3, sketch a graph of the function on the interval t equals 0 to t equals 5,000. I am going to go ahead and graph this before answering number 2, because then I can just use my graph and trace to the value of 1,000. So let's do that real quick. And so since it's giving us 0 to 5,000 for our domain that we're interested in, I'm just going to go ahead and go to my my window and say x min is 0, x max is 5,000, and then I'm going to hit zoom fit. And it is going to give me an absolutely perfect graph that looks like this. And then I'm going to trace to the value of 1,000, and it's going to tell me that the y value there is 16.297. And remember, our equation is in grams, so after 1,000 years, if you start with 25 grams of radium, after 1,000 years, it will be down to 16.297 grams. But think about what just happened. This is pretty cool because we essentially just answered a half-life problem like we did earlier, but we didn't even have to find the rate of decay. That's pretty cool. So let's think about this equation here. This equation is saying that the amount after time t is equal to the principal amount times 1/2 to the power of t, the number of time units, typically years, but not necessarily, t divided by the half-life, which I'm just going to call h. And that is different than what we've seen before, because we've been looking at the PERT equations, p times e to the r times t, and now we have some weird division up there. But this allowed us to solve the problem without finding the rate. That's really cool. And the question is, are these two methods actually the same? Well, the answer is yes. And I challenge you to figure out why that is. Okay, have you figured it out yet? If not, you're taking too long, and I'm going to show you because I think it's actually pretty cool. And we have all the tools necessary to take a look at it. So let's think about what we were doing. When we had a problem before, we were using the equation we're used to, A equals P times E to the RT, the PERT equation. So I don't have any idea where I left that sentence off. But I want you to compare what we just used, A of t equals p times 1/2 to the power of t over h. Compare that to what we have used in the past, A equals p times e to the power of rt. And notice that the t is the same in both. The A of t is the same in both. The p is the same in both. The top equation doesn't have a rate, and the bottom equation doesn't have a half-life. The top equation has a 1/2, and the bottom equation has an e, the natural number e. But think about our process. Typically, we knew the half-life, the number of years, and so we took this equation and said that after the amount of time specified for the half-life, the A of t value would then be 1/2, half of the principal amount, so 1/2 the principal amount, and then we had times E, and I just scoofed up because we got the 1/2 by taking the amount after t time units and dividing it by the starting amount to get the 1/2. So we got 1/2 equals e to the power of r times t, and for t we're saying it was the value of the half-life. And then we took the natural log of both sides, natural log of 1/2 equals e, let's do this, equals the natural log of e to the RH, and then I can plug it and bring that RH out front, and then ln of e is 1, so I get the ln of 1/2 equals r times h, but I'm going to divide by h, just like that. And so I get my rate is equal to the natural log of 1/2 divided by the half-life. And then we took that value and plugged it into this equation to figure out that A of t, the amount after time t, was going to equal the principal amount times e to the power of our rate. And now instead of writing r, I'm going to write what my rate actually is, because my rate is the natural log of 1/2 divided by h, the half-life, and then we multiplied that by t, whatever our time was. But let's rewrite this equation a little bit. Let's get A of t equals p times e to the natural log of 1/2 times t over h. Notice all I did was move that h over there. Because now I have e to the power of the natural... Oh, wait, no, I can't do that yet. Sorry, I'm getting excited. But I have p times e to the ln of 1/2 times t over h. But think about what you can do with exponents. We could think of this as that situation right there. And e to the power of ln to the 1/2 is just 1/2. So then I have my t over h right there. And voila, A of t equals p times 1/2 to the power of t divided by h, just like we used a moment ago. Isn't that cool? I think that's pretty nifty. So we're going to do one last problem together today. This says, solve the following quadratic type exponential function. So we are going to use some rules of exponents here to rewrite this as e to the power of x squared minus 3e. It's not where I meant to put my parentheses, meant to do minus 3e to the x plus 2 equals 0. And then now let's make a little substitution here. Let's say let e to the power of x equal, I don't know, let's go t, whatever. And then we can say then t squared minus 3t plus 2 equals 0. And now it looks a lot prettier, and we can factor this, and we can say that we're going to factor this into two terms right there, two linear factors, and it's going to factor as t plus 3, and I lied, it's totally not going to be that. It's going to factor as t minus 2 times t minus 1. Sometimes I can't do math very well, because negative 2 times negative 1 is positive 2, and negative 2 minus 1 is negative 3. So that factors correctly, and we get the two solutions, t equals 2, and t equals 1. But remember that t is e to the x. So really what we have is e to the x equals 2, and e to the x equals 1. So how do we solve this? Well, we're going to solve it by rewriting these as logs. So for the first one, to get the x, we're going to get x equals the natural log of 2. And that's going to be our answer for that. And then for the second one, we're going to get x equals the natural log of 1, which is 0. So our two solutions to this are the natural log of 2 and 0.